If logic gates are the neurons of a computer, the ALU, the Arithmetic Logic Unit, is the muscle. It's the part of the CPU that actually does the math. But how do you go from a simple NAND gate to a machine that can calculate the physics of a universe? Think back to how you first learned to add. You stack the numbers, sum the column, and if the result is 10 or more, you carry the 1. Binary addition follows the exact same rules. It's just limited to 2 digits, not 10. Let's look at it one column at a time. Every pair of bits can only be arranged in a few ways. 0 plus 0 is 0, no carry. 1 plus 0, or 0 plus 1, is 1, still no carry. But 1 plus 1? That's 10 in binary. We put down the 0 for the sum and carry the 1 to the next column. So for every column we process, we need 2 inputs and 2 outputs. Let's see if we can build this using the gates we already know. First, the sum. If you look at the pattern, it's a perfect match for the XOR gate. It's only 1 when the inputs are different. Now for the carry. We only need a carry bit when both A and B are active. That's the AND gate. Perfect. This circuit we just built, it has a name, the half adder. And while it's a brilliant piece of logic, it has one major limitation. It can send a carry bit, but it has no way to receive one. Every column of addition after the very first one needs a third input, the carry in from the previous step. To fix this, we don't need a new complicated gate. We just need to chain 2 half adders together. Think of it as a 2-step process. First, we add our main inputs, A and B, to find their initial sum. But we aren't done. We take that result and feed it into a second half adder. This is where we finally add that carry in wire. The output of this second box is our final sum. Now, you might notice that both boxes have a carry wire. Do we need 2 different carry outputs? Actually, no, because it is physically impossible for both to be 1 at the same time. Think about it. If the first box generates a carry, it means its inputs were 1 and 1. That leaves its sum as 0. Adding a 0 to a carry in can't possibly create a second carry. It's an either-or situation. Either the first addition created a carry or the second one did. So we just plug them both into an OR gate to catch the result. Perfect. We now have a full adder, a single unit that can handle a whole column of binary addition. It takes our 2 main bits, A and B, adds them to the carry in from the previous column, and then spits out a sum and a new carry out for the next step. But computers don't just add single bits, they handle massive numbers. So how do we scale up? Suppose we want to add 2 4-bit numbers, 7 and 3. To add them, we simply line up 4 full adders in a row, 1 for every column of the math. For the first column on the right, we feed the last bits of each number into our first adder. It processes the math, 1 plus 1, and drops our very first result, 0, with a 1 left over to carry. Now, for the second column, we provide the next 2 bits. But remember, this column needs to know if the first column carried a 1. So we physically wire the carry out of the first adder into the carry in of the second. This second box adds the bits together, along with that carry, and gives us our second result, 1. We repeat this chain reaction for the third column, and then the fourth, always passing that leftover carry bit to the next neighbor. When the signals settle, we have our final answer, 1010, which is 10 in our normal decimal system. This is called a ripple carry adder, because the carry bit literally ripples across the circuit from one adder to the next, like a wave, until the calculation is complete. So, our ripple carry adder is a masterpiece at adding. But how do we make it subtract? In binary, we don't have a minus sign. To a computer, 7 minus 3 is the exact same thing as 7 plus negative 3. But how do we even represent a negative number? We use a trick called 2's complement. Take our numbers 7 and 3. First, for the 3, we flip every bit, turning 1s to 0s and 0s to 1s, to get 1, 1, 0, 0. Then, we just add 1. This gives us 1, 1, 0, 1. In the computer's world, This string of bits effectively is -3. If we add this to our 7 and ignore the extra carry bit at the very end, the result is 0100, which is 4. Now, how do we build this into our circuit? We already have an adder, so we just need to prep the second number before it enters the boxes. We can place NOT gates on all the B input wires to flip the bits automatically. But wait, we still need to add 1 to finish the 2's complement trick. Remember that carry in on the very first full adder? Usually, it's just sitting there at 0. If we plug a 1 into it, it effectively adds that missing 1 for us. But we don't want a machine that only subtracts. We want one that can do both. This is where the XOR gate comes to work. Think of an XOR gate as a smart toggle. If we feed a 0 into the control pin, the XOR gate lets our data pass through completely unchanged. It stays exactly as it is. But if we flip that control pin to a 1, the gate instantly transforms into an inverter, flipping our input to its opposite. This is perfect! We can replace our static NOT gates with these XOR gates and link their control pins to a single mode wire. If we connect that same wire to our first carry-in, we get a brilliant result. Whenever this signal is 0, the circuit adds our 2 numbers. But the second we flip it to 1, the whole machine becomes a subtractor. Perfect! We've just finished our first major module, the adder/subtractor. It takes in 2 4-bit numbers and a mode bit to decide the operation. It outputs a 4-bit result, plus 1 extra wire, the carry-out. If this lights up, it means our result was too big to fit in 4 bits, a situation called an overflow. Just keep that in the back of your mind for later. Now, to keep things from looking like a mess of wires, whenever we have 4 paths moving in parallel like this, we're going to merge them into one thick line. This little symbol indicates it's a 4-bit bus. Much cleaner. In most computers, an ALU is split into 2 neighborhoods, the arithmetic unit and the logical unit. We've already built the heavy lifter for the arithmetic side. While modern chips have dedicated circuits for things like multiplication, they're really just complex arrangements of the same logic gates we've been using. For our build, we'll just have the adder/subtractor module in the arithmetic unit. So, let's move into the logical unit. This area handles bit-by-bit comparisons. An AND module, for example, just runs an AND gate on every pair of bits simultaneously. For this ALU, we'll include an AND unit and an XOR unit. But logic isn't just about comparing, it's also about moving. We're going to add binary shifters. In a right shift, we take our 4 inputs and slide them over by 1 slot, filling the empty space with a 0. We can do the same in the opposite direction for a left shift. Now, while a real CPU might use our second input, B, to decide how many slots to shift, we're going to keep it simple and just shift by 1 bit every time. Whew, that was a lot, but we're almost done. We have our toolkit. We can add, subtract, compare bits with AND and XOR, and even shift them around. But here's the problem. We have all these different modules, but only one output. How does the computer pick the answer it actually wants? Meet the multiplexer, or the MUX. Think of it like a railway switch. You can have multiple tracks coming in, but only one track leaving. The MUX uses select wires to decide which incoming train gets to pass through. If we pass 0 to our select wire, it selects the first input. 1, it lets out our second input. 2, it lets third input. And lastly 3, it lets out our fourth input. To control these multiplexers, we use an opcode. For our ALU, this is a 3-bit code we'll call C1, C2, and C3. Now, here is the secret to how a CPU actually works. When we send our numbers A and B into the ALU, they don't just go to one place. They flow into every single module at the same time. The adder is adding, the XOR unit is comparing, and the shifters are sliding. It's a chaotic race where every unit produces an answer simultaneously. We use our opcode as a decision tree to filter out the noise. The first bit, C1, is our master switch. If it's a 0, the ALU knows it's doing a logical operation. If it's a 1, it's doing an arithmetic operation. This bit allows our final MUX to ignore half the circuit instantly. But we need to get more specific. Inside the logical unit, we have 4 tools, AND, XOR, and our 2 shifters. This is where bits C2 and C3 come in. Since 2 bits can create 4 different combinations, We use them to point our mux exactly at the module we need. On the arithmetic side, we use those same bits, C2 and C3, for a bit of a hardware hack. We want to be able to increment and decrement, adding or subtracting 1, without building a whole new circuit. So, we place a mux on the B input. If bit C2 is a 0, it passes our number B through normally. But if C2 is a 1, the mux ignores B and passes the value 0001 instead. At the same time, we wire bit C3 directly to our mode pin. If it's a 1, the circuit subtracts. If it's a 0, it adds. By using these two bits as a team, we can recycle our one heavy-duty adder to do 4 different jobs. But the ALU doesn't just give us a number. It also triggers 3 flags to tell us how the calculation went. The negative flag simply watches the far left bit of the result. If it's a 1, the negative flag turns on. This works because according to 2's complement, if the leftmost bit, also known as the most significant bit, is 1, then the number is considered negative. The carry flag catches any overflow bits if the math got too big for our wires, which, if you remember, we take from the carry out of our adder. And lastly, the 0 flag. If you remember, NOR gates output 1 only when all inputs are 0. So here we use a 4-input NOR gate to sniff the result wires. If there is absolutely no electricity, meaning every single bit is a 0, the 0 flag turns on. Now, is this exactly how a professional modern processor works? Not quite. Engineers have spent decades finding hyper-efficient ways to squeeze these gates together. But at its heart, the logic is identical. It's just a series of simple switches, working together to make the complex world we see on our screens possible, one bit at a time. So let's test our ALU. To see if two numbers are equal, we just subtract them. If we feed 5 and 5 into the ALU and hit subtract, the result is 0, which triggers the 0 flag. That 1 on the flag is the computer's way of saying, yes, they match. Same for checking if 4 is smaller than 5. Subtract them, get a negative result, and the negative flag turns on. Simple, but it's the foundation of every decision a CPU makes. Now, this is all great on paper, but if you want to get your hands dirty, you don't need a breadboard or a soldering iron. You just need a logic simulator. Personally, I use Digital Logic Sim by Sebastian League. Let's hop into the sim to prove this actually works. And no, this isn't a sponsor. I have 7 subscribers. I don't need to clarify that. Enjoy the time lapse.